Je vous salue à tous. Bienvenue à la leçon d'aujourd'hui. Je m'appelle professeur Kihwa. Je suis professeur de chimie et biologie. Okay. So welcome all viewers, all students, and every other person that has come in and those are yet to come in. I want to take this opportunity to thank you all for tuning in, and also thank you for having given me unwavering support in terms of viewing, in terms of sharing my videos. So welcome to today's lesson. As usual, this is a Chemistry Wednesday. We always have our lectures or rather lessons from 1 to 2 p.m. for all high school students. So we have been doing structure and bonding, and those who have viewed already my videos, we have done ionic bond. So we started by doing ionic bond. We looked at the structures of ionic bond and the properties that or characteristics of those compounds. In our second discussion on structure and bonding, we also talked about covalent bond. We have discussed single covalent bond, double covalent bond, and triple covalent bond. So today I want us to continue with the same covalent bond. I think we left here last time when we had completed looking at structures of ionic bond. So maybe a few things that I need to highlight as we start today's lesson is we said that covalent bond is a bond between non-metals. It is where non-metals come together, they bond in order to form a molecule. So we say hydrogen molecule, okay, hydrogen molecule, oxygen molecule, nitrogen molecule, etc. Fluorine molecule for this, chlorine molecule, and the rest. Something that I need to point out clearly is that when we say hydrogen molecule, we are actually saying we have two atoms of hydrogen in this molecule. We have two atoms of oxygen in this molecule. These are two atoms of nitrogen, two atoms of fluorine, two atoms of chlorine, etc. We also have ozone, which is O3. We have ozone, which is O3. So this ozone, in other words, there are three atoms of oxygen to form an ozone molecule. So this actually is all about molecules, and we said the number of atoms making the molecule are called or is called atomicity. So that's what we did in our last lesson. Today, I want us to continue further with this topic, and I want us to look at structures involved or structures of covalent bonded compounds. Structures of covalent compounds. Structures of covalent compound. As we continue, let me mention that this is my way of teaching. There could be several ways of teaching, but actually the concept is the same. So structures of covalent bonded compounds. Covalent bonded compounds, when we looked at ionic bond, when we looked at ionic structures, we talked about only one ionic bonded compounds. Ionic compounds have one structure, which we said is giant ionic structure. So giant ionic structure for ionic bonded compounds. Now for covalent bonded compounds, we have two types of structures. There are two types of structures. One is simple molecular structure. Simple molecular structure. And two, we have giant atomic structure. So we have simple molecular structures for simple molecules, and then we have giant atomic structure. So let us look at each one of them separately. So we start with simple molecular structure. That is one. Simple molecular structure. You remember we said a structure is a certain pattern, a repetitive pattern that bonding molecules or bonding atoms form. So simple molecular structural compounds. Now these simple molecular structures involves molecules, simple molecules like hydrogen molecule, chlorine molecule, oxygen molecule, nitrogen. Those simple molecules form simple molecular structures. I want us to look at, to use an example of iodine. Let us use an example of iodine. Now, if you look at iodine gas is written like this. We said when it is written like this, then it means 2 atoms of iodine in one molecule. So therefore, this is the same as saying this iodine and iodine. This one here, as we said in our last lesson, represents a covalent bond. That is an X and a dot. As we say, this is a pair of electrons. So in iodine molecule, we have iodine atom. Iodine atoms, 2 iodine atoms to form an iodine molecule. In this particular case, for us to have a crystal of iodine, or a solid of iodine, or liquid, if it is liquid. Now, for us to have this, then we need several molecules of iodine. Okay, we need several molecules, whereby each molecule contains 2 iodine atoms. So now, when we have a crystal, let's say a crystal, or a solid, a piece of a solid of iodine, it contains several iodine molecules. So that is like this molecule is linked to another molecule of hydrogen. Okay, and this one is linked to another. This one is linked to another. So that this is I2 linked to another I2 etc. Okay, so we have, this is one molecule of iodine, another molecule of iodine, another molecule of iodine, another molecule of iodine. So these molecules are linked together in order to form a simple molecular structural compound of iodine. Now, as we said in our last lesson, this one is covalent bond. So this bond holding the 2 atoms together is called covalent. Okay, so this one is covalent bond. This one also is covalent bond. This one also is covalent bond. This one is covalent bond. Okay, this is a bond which holds 2 atoms of either same kind or different kinds together, where, as we said, these ones share electrons in order to be stable. Now, this other bond that is linking one molecule to another molecule, this one is called weak van der Waals. It is weak van der Waals forces of attraction. Okay, so this is a weak van der Waals force of attraction. This is also weak van der Waals forces. Okay, this one is weak van der Waals force of attraction. This one is weak van der Waals forces of attraction. In other words, this covalent bond is intramolecular, between the atoms. So it is intramolecular or interatomic, if you like. This is interatomic. Now this one is intermolecular. Weak van der Waals force of attraction is intermolecular. So that is it. So what we can conclude from that, or what we can draw from this, we can say simple molecular compounds have weak van der Waals forces of attraction between the molecules. Okay, between the molecules. So that this one is a molecule, this one is a molecule. Between the molecules is called intermolecular. Okay, so it is weak van der Waals force is an intermolecular force of attraction. Now most of these compounds, most of them, they are either gases, most simple molecular compounds are gases, liquids, or solids which sublime. When heated. Now, most of these simple molecular compounds are gases like oxygen, nitrogen, chlorine gas, fluorine gas, etc. So most of them are gases. Some are liquids. For example, bromine. We have bromine. Bromine is a liquid. Is an example of a simple molecular compound. Or solids. Now, these solids sublime when heated. Examples of this solid include this iodine. Iodine is a solid at room temperature and it sublimes when it is heated. We also have sulfur. Sulfur is a simple molecular compound and when it is heated, it sublimes. So these are compounds, simple molecular compounds. So we are saying they have weak van der Waals force of attraction between the molecules. We also have another factor here. We shall look at it after this. And then most of these molecular compounds are gases, liquids, or solids at room temperature. The examples I've given you, those ones which are gases at room temperature, we have chlorine, fluorine, oxygen, nitrogen, okay, hydrogen. Those ones are gases at room temperature. And then liquids at room temperature, example is bromine liquid. Bromine is a liquid. And those ones which are solid, they are solids. The characteristics of those solids which are simple molecular is that they sublime when heated. Example is this particular case here. So in this, before I take this paper out, you need to know here that using iodine, we have used iodine to differentiate between covalent bond and weak van der Waals forces of attraction. So that covalent bond is interatomic or intramolecular. Interatomic, that is between the molecules, or intramolecular, in the molecule. So inside this molecule, we have covalent bond. It is holding the two atoms together. Weak van der Waals force of attraction is intermolecular. Inter is between the molecules. Now, this one is in the molecule between the atoms. This one is between molecules. So this one is called intermolecular forces of attraction. That's why when we were looking at characteristics of group 7 elements, halogens, we said halogens, their melting and boiling points increases down the group. Why does it increase down the group? It increases that group because there is increase in the strength of intermolecular forces of attraction. So that is where intermolecular comes in. So that is simple molecular compounds. Let us continue with the same. Now, something else also we need to know about these simple molecular compounds is that they are simple molecular compounds are poor conductors of electricity. They are poor conductors of electricity. The reason is because since they don't have, or they do not have, mobile ions or electrons. Now, in any case, we have said in our previous lessons that for any substance to conduct electricity, for electricity conduction by any metal, any substance, it requires to either have mobile ions or delocalized electrons. Absence of this means the substance does not conduct electricity. For example, we said ionic compounds conduct electricity only in liquid or aqueous state. The reason is because they have mobile ions. Again, all metals conduct electricity. Why? Because they have delocalized electrons. Now, molecular compounds, they do not have mobile ions. They do not have mobile electrons. Therefore, they are poor conductors of electricity. The simple examples of these molecules that we have in our kitchens are like sugar. Okay, sugar is simple molecular. Flour is simple molecular, so they do not conduct electricity. But table salt is sodium chloride. Sodium chloride is ionic compound, so it conducts electricity in liquid or aqueous state. So these are simple molecular structures. They are poor conductors of electricity. Another thing also is that they are insoluble in water but soluble in organic solvents. They are insoluble in water, but they are soluble in organic solvents. Normally, solubility in chemistry, we have solubility in water. We have two types of solvents, okay? Just to mention, we have two types of solvents. We have polar. We shall look at it shortly. We have polar and we have non-polar. Now, polar solvent is water. Water is a polar solvent. We shall discuss it after this. So, water is a polar solvent. Organic solvents, okay? So, the rest, the organic solvents are said to be non-polar. We shall look at the reason. So, organic solvents, you know, some of these include propanol, include methyl benzene, and the others. There are so many of them. They are called organic solvents. So, if a substance is soluble in water, automatically it is not soluble in organic solvents, and the opposite is true. If it is soluble in organic solvents, then it is not soluble in water. Example of these is simple molecular compounds. Most of them are insoluble in water, but they are soluble in organic solvents. So those are that is simple molecular compounds. They are insoluble in water. They are poor conductors of electricity. We already have said most of them are gases at room temperature. Most of them are gases. Some are liquid, some are solids, but most of them are gases. So we can also say they have low melting and boiling points. They have low melting and boiling points. The reason as to why they have low melting and boiling points is due to the presence of weak van der Waals. Forces of attraction. So since they have weak van der Waals forces of attraction, then they are poor. They have very low melting and boiling points. And you will remember we have said most of these substances are gases at room temperature. Only a few of them are solids, a few of them are liquids. So because most of them are gases, they are gaseous, in gaseous form, then they have weak van der Waals force of attraction. That means they have very low melting and boiling points. As we said also in our first lesson, the stronger the forces of attraction, okay, the stronger the forces of attraction, the higher the melting and boiling points. And also, the weaker the forces of attraction, the lower the melting and boiling point. So because the forces of attraction here are weak, then low melting and boiling points. So that is simple molecular compounds. You can give examples of simple molecular compounds that we know. We have said sugar. Examples. We have iodine, sugar. Now name the others: hydrogen, oxygen, chlorine, fluorine, bromine, etc. There are so many. Also the fuel, the crude, the substances separated from crude oil also are other examples of liquid. Liquid, the petrol, diesel, those ones, they are simple molecular liquids. So those are that is as far as simple molecular structure is concerned. We remember that it forms simple molecule. So number 2, we said that is number 1 type of covalent bond. So we said here at the beginning that we have 2 types of structures for covalent bond. We have simple molecular and we have giant atomic. So let us look at giant atomic structure. Oh, before we go to giant atomic, before we go to giant atomic, we have talked about intermolecular forces of attraction. Intermolecular. We have said intermolecular forces of attraction are forces of attraction. These are forces of attraction between the molecules. Okay, forces of attraction between the molecules. There are 2 types that we talk about in Form 2. We have types. We have weak van der Waals, forces, and hydrogen bond. So we have 2 types of intermolecular forces of attraction. There are others, but what we talk about in Form 2, we have weak van der Waals forces of attraction and hydrogen bond. So we have talked about weak van der Waals. Now let us talk about hydrogen bond. Hydrogen bond. Hydrogen bond. Hydrogen bond, this is an intermolecular force of attraction. It is an intermolecular force of attraction between a more electronegative atom and hydrogen. It is an intermolecular force of attraction between a more electronegative atom and hydrogen, as in where an electronegative atom bonds to a hydrogen. These electronegative atoms, examples of these electronegative atoms, more electronegative atoms include oxygen. Okay, another electronegative is nitrogen. Okay, another electronegative is fluorine and others. Okay, so these are examples of electronegative atoms which bond to hydrogen in order to form a hydrogen bond. This is seen in functional groups that we talk about in organic chemistry. The nitrogen and a hydrogen to form amine or amino group. Oxygen forms OH and carboxylic acids and so on. So that is these are examples of compounds with hydrogen to form a hydrogen bond. Maybe we can talk about an example of hydrogen bond in water. Example of hydrogen bond in water. Okay, let me turn over. Now you are aware that water molecule is H2O. Okay, this simply means two atoms of hydrogen and one atom of oxygen. Okay, to form a water molecule. So this molecule contains two hydrogen atoms and one oxygen atom. The bonding here is we have one oxygen, we have one hydrogen, we have one hydrogen. Remember this? We said this one is a covalent bond. So this is a covalent bond and a covalent bond representing two electrons. So we have two electrons here, we have two electrons here. Now this is one molecule of water. For example, a drop of water, we have very many molecules. This is just one molecule. So that drop of water contains very many molecules. So we have another, let's say we have another molecule here. Another one, there are so many of them. Let me use these two. So here, oxygen, as we have said in our previous point to note, is that oxygen is more electronegative. What do we mean by that? When we say oxygen is more electronegative, we mean oxygen, this is a shared pair of electrons. This is a shared pair, shared pair, shared pair, shared pair, like that. Now, this oxygen tends to pull. It tends to pull the two shared pair of electrons more to itself than hydrogen, because hydrogen is electropositive, oxygen is electronegative. So this is electronegative. It tends to pull the electrons, the shared pair of electrons, to itself. In so doing, it creates partial charges. Maybe we can note that. So oxygen tends to pull the shared pair of electrons more to itself. Okay, tends to pull the shared pair of electrons more to itself than hydrogen, more to itself than towards hydrogen. Maybe we could have said hydrogen bond in water. Let us put this. Let us just add to our point here. hydrogen bonding in water molecule. Are we together? Hydrogen bond in water, so that we are discussing water. All right. So this, so oxygen is more electronegative, so it tends to pull the shared pair of electrons more to itself than towards hydrogen. So let's say since oxygen is more electronegative, you will pardon my pens, they are almost completing a circle, so I need a sponsor for this. Yeah. Okay, so oxygen is more electronegative, so it pulls the shared pair of electrons more to itself than towards hydrogen. Now, in so doing, this creates a partial negative charges on oxygen and partial positive charges on hydrogen. So this creates a partial negative charge or partial negative charges on oxygen and partial positive charges on hydrogen. So let's go back here. So now in this particular molecule here, we have partial negative charges. So we say this one is delta negative. Okay, this is delta negative. Delta is a D with a bukia. Okay, yes, a D with a bukia is called delta. So delta negative, this one is delta positive. This one is delta positive. Okay, hydrogen delta positive. Hydrogen delta positive. Oxygen delta negative. All right, that is what we call partial positive and partial negative charges. Why do we have partial charges? Because oxygen is more electronegative. It pulls the two electrons to itself, leaving hydrogen a bit far from the two electrons. So it looks more like oxygen gains and hydrogen loses. It does not actually lose, but it looks something like it loses an electron and this one gains. So in so doing, it creates partial negative and positive charges. So now this molecule is attracted to this molecule. So we have the negative is attracting positive. So as we said that like charges do what? Yes, and unlike charges do what? Correct. So this one attracts to hydrogen. This one hydrogen attracts, links to oxygen like that. So the negative attracts the positive like that. To form this one now forms maybe a drop of water or something like that. And another molecule here, the same thing. Now this one here, in between these molecules, this bond is covalent. All right, this covalent. This one is covalent. Okay, it is inter. Okay, remember inter. Not inter. Intra. This is between the molecule or inside the molecule, between the atoms, between hydrogen and oxygen atom. Covalent. This is also covalent. This is covalent. Now this one is hydrogen bond. This one is hydrogen bond. Okay, intermolecular. So this one is intermolecular. Just like weak van der Waals forces of attraction, hydrogen bond is intermolecular. So that is bonding in water. So you note these points. So that is how it looks like. This one molecule, this another molecule. Between the molecules we have hydrogen bonds, and then inside the molecule between the atoms, we have covalent bonds. Okay, so that is it. Let us continue with something more. So we can also say that this is what we wrote in our previous point. This makes water a polar solvent. This makes water a polar solvent. So it is a polar solvent because there are partial positive and partial negative charges there. So water is a polar solvent. So that is what we can say about polar solvents or hydrogen bond. That is an example of hydrogen bond, an example of intermolecular force of attraction. Okay, so I hope that is okay. Examples, other compounds that have hydrogen bonds. Other compounds with hydrogen bonds include the alkanols and alkanoic acids. Let me just write them in general. You can give examples of alkanols: methanol, ethanol, propanol, propanoic acid, methanoic acid. So let me say include alkanols and alkanoic acids. So those ones are polar solvents. Okay, so I think we are done with hydrogen bond. So let me go to giant atomic structures. Correct. So let me go to giant atomic structure. Giant atomic structure. So this is where compounds have strong covalent bonds. These are compounds in which they have strong covalent bonds in between their atoms. Between the atoms. When we say giant, just like we said, giant ionic structure. So when we say giant atomic structure, then these are compounds that have very strong forces of attraction. Examples of these is diamond, graphite, and 3 silicon 4 oxide. We have these are 3 examples of compounds with giant atomic structure. These are diamond, graphite, and silicon. Let us look at the 2. Let us begin with diamond and graphite. So we can say diamond. Now these pens are filled up. So diamond and graphite are allotropes. Of carbon. So diamond and graphite we say are allotropes of carbon. Thank you, my producer. So they are allotropes of carbon. We can say allotropy is the existence of different forms of an element in the same physical state. Existence of different forms of a compound in the same physical state. So we say allotropes of carbon. So we are saying when you are asked to define allotropes, then you say allotropes are different forms of an element in the same physical state. So these two are allotropes of carbon. Mark that. Maybe we can say other elements that exhibit allotropy are sulfur and phosphorus. Sulfur and phosphorus. So we have three elements that exhibit allotropy. Okay, three elements: carbon, okay, sulfur. Sulfur does not have an E, sorry. Sulfur ends with R. So we have carbon, sulfur, and phosphorus. Allotropes of carbon, we have said graphite, diamond. Allotropes of sulfur, as will be done in Form 3, is monoclinic sulfur and rhombic sulfur. Then phosphorus, we have white phosphorus and we have red phosphorus. So those are substances or compounds, elements that exhibit allotropy. So let's continue with diamond and graphite. So diamond and graphite are allotropes of carbon. Maybe we look at each one of them. Let us begin with the diamond. Diamond is one of the allotropes of carbon. Now in diamond, four electrons in carbon, 4 electrons of carbon are used in bonding, and each carbon is bonded to other 4 carbons. So in diamond, 4 electrons in carbon. You are aware that carbon is atomic number 6. Carbon is atomic number 6. Electron configuration is 2, 4. So the valence electrons are 4. Okay. So in diamond, all the valence electrons are used in bonding. As we said, valence electrons are the electrons in the outermost energy level. So valence electrons for carbon are 4. Now here, all the 4 electrons are used in bonding. None of them is left delocalized. Okay, so maybe we can say none of them is left delocalized. None of the electrons. So none of them is left delocalized. And therefore, diamond is a poor conductor of electricity. So diamond is a poor conductor of electricity because all the 4 electrons in carbon are used. None of them is left delocalized. Already I've talked about conduction of electricity, being a good conductor and a poor conductor. So in my discussion, I will give you the discussion and the characteristic at the same time. So I hope you get through it. 2, about diamond is that it forms a tetrahedral structure. We have said when carbon bonds to other 4, so it bonds to another 4 with other 4 to form a tetrahedral structure. This consisting of pure, strong, covalent bonds. Consisting of pure, strong, covalent bonds. So because it consists of pure, strong, covalent bonds, then we can say thus diamond is the strongest, let's say hardest, not strongest, is the hardest natural substance. For your information, diamond is the strongest natural substance on the surface of the earth. It is even used to drill boreholes, to drill through rocks, because it is hard. Why is it hard? It is hard because it consists of pure, strong, covalent bonds, which enables it to form tetrahedral structure. Also, it also have very high melting and boiling points. It has high melting and boiling points. The reason is because the bonds between it are strong covalent bonds. So that's what we can say about diamond. There are other things about diamond. You can find out by reading more about it. It's very interesting. So it has this. It also have shiny appearance. it has shiny appearance. That's why it's used. Shiny appearance and used in making jewelry. Jewelry. Okay, it's used to make jewelry, bangles, necklaces, all those. The vipuli, yes, the ring, okay, wedding rings and all that. So many of them. Why? Because diamond has a shiny appearance. ETC. So that is diamond. Graphite, number 2, is graphite. Another allotrope of carbon. So in graphite, the three electrons of carbon are used in bonding. So in graphite, 3 electrons of carbon are used in bonding. So if 4 and 3 is used in bonding, what does that mean? 1 is left delocalized. Now, because of the one that is left delocalized, so we can say 1 is left delocalized. And now this enables graphite to conduct electricity. So graphite is a good conductor of electricity. By the way, graphite is the only non-metal which conducts electricity, and that is enabled by the presence of the delocalized electron. Also, this is why graphite is used as an electrode in dry cells, electrochemical cells, and those. So also we can say graphite forms hexagonal structure. Hexagonal structure where one layer is held to another layer by weak van der Waals. By weak van der Waals forces of attraction. One layer between the layers, we have weak van der Waals force of attraction. Maybe just a simple illustration is if we have this. This is hexagonal, so we have one carbon here, carbon, like that. We have another layer just a rough sketch of it. We will have another layer down here. Let me just use this. to illustrate. So between this layer, between them is weak van der Waals forces of attraction. So this one is weak van der Waals forces of attraction. Of course, the corners or the vertices, as you say, the vertices are carbon atoms. So carbon, like that, the corners are carbon atoms. And then between the layers, so this is one layer, this another layer, between the layers is weak van der Waals forces of attraction. So that's why we have said one layer is held to another layer by weak van der Waals forces of attraction. Our last point there. So the layers slide over each other. The layers slide over each other due to weak van der Waals forces of attraction. So due to weak van der Waals forces of attraction, the layers slide over each other. Hence, graphite is used. Graphite is used as a lubricant. That is one. As a lubricant. It is also used in manufacture of pencil. Manufacture of pencil. Why? Because the layers are able to slide over each other. As you use a pencil, when you are writing using a pencil, you write, and what enables you to write is that the layers of the pencil contains graphite. Those layers slide. So as they slide over each other, they remain on paper. So that is one use of graphite. It's also used as a lubricant because it lubricates, because the layers also slide over each other. Graphite have low melting and boiling point compared to diamond. It has low melting and boiling points compared to diamond. The reason is because of the presence of weak van der Waals forces of attraction. Now for silicon 4 oxide, number 3, giant atomic structure. Diamond, graphite, silicon 4 oxide. Let me just mention, this is also a compound which has giant atomic structure, is silicon, where 2 oxygen atoms is bonded to 1 silicon atom. So folks, that is it for today. Our lesson today has been structures involved in covalent or involved with covalent bond. Thank you for watching. Share the video if you also like my YouTube page, Teacher Kirwa. Go there, subscribe to it. There are more videos on that website. Otherwise, until next time, I wish you a blessed week. Bye bye.